How complex can it to be run a single instruction? If the processor is a Intel iAPX 432, the answer is very complex. Hello, my name is Mark, and in this video I will walk you through the process of booting the APX 432 and everything that is required just to run user code. If you have not heard about that obscure chip, you can watch my previous video in which I gave a brief introduction to that fascinating phenomenon from the 80s. For the current video, it's important to say that the CPU is object-oriented and implemented some parts of the operating system's job in silicon. You might wonder if the APX can perform a cold boot when the memory is completely blank. The answer is no. The APX relies on attached processor, like an 8086, to prepare data structures in memory before sending an interprocessor signal to wake up the GDP. That means we need to manually prepare a bunch of objects for the processor itself. Processes, ports, execution domains, context, and of course the segments and objects tables that describe them. Sounds fun. Let me remind you that I built a memory controller with an FPGA and external SRAM so I can monitor every bus transaction. My strategy was simple. Record everything the processor tries to access and fill in whatever is missing. Let's dive into that access log. I already covered the very first request in the previous video, but let's repeat them quickly for completeness. GDP starts by checking the interprocessor communication status in interconnect register 2. If there is a pending IPC message, the CPU wakes up and tries to read it. APX 432 was designed for multiprocessor systems with shared memory, but each processor still needs its own private structures. Solution was a single global table that holds references to all processor objects. CPU finds its own entry by using its processor ID from interconnect register 0 as an index in such table. The next step is locating that global object table. There is an initial object table directory, and the first descriptor points to the processor's object table. It is worth pausing to talk about the descriptor format, because the APX accesses them constantly. Almost every object access requires a slow two-level lookup. First, the CPU finds the object table, and then the descriptor for the referenced object. Even with caching, it's not very performant. The most common type is the storage descriptor. The others are either simple or rarely used. So let's concentrate on them on storage descriptors. Some fields are obvious: descriptor type, base address, length, etc. But a few bits are really important. Firstly, there are two kinds of segments: data segment and access segments. Access segments are exclusively used to keep references to objects. The APX system doesn't have row pointers. Instead, every pointer acts as a capability. It encodes extra permission information and references a storage descriptor rather than a raw memory address. The GDP constantly checks permissions by comparing capabilities against segment descriptions. Another two fields that require additional attention are valid and storage associated. They look similar, but the timing of the check is different. If a segment is not valid, you cannot even create a pointer to it. If it is valid, but has no storage associated yet, you can create a pointer. The error only occurs when you actually try to access it. Input-output log bit is for the interface processor. I am not using it, so I don't need to implement support for that field. The altered and accessed flags are set by the GDP, whenever it writes or even just reads the segment. For some reason this matters, so the processor spent 2 extra memory cycles to update them. You can notice the read modify write bus flag in the log. Those 2 cycles form one atomic operation. GDP guarantees that nothing else can touch the logged address in between. Another similar flag is the reclamation field. If it is 1, then there is a pointer to that segment and it cannot be freed. Additionally, the level number controls garbage collection policy. Yeah, the garbage collector is part of the processor itself. Finally, the system type field tells the processor what kind of system object this segment represents. You can begin to see how much work the CPU does to to just support its own object model. After already mentioned setting the altered and accessed flux, the GDP reads the physical address of the object table containing processor segments. For some reason, this is done as 3 separate bus operations instead of a single 10-byte access. So in total it can be 5 bus requests instead just 2 or 3. Very efficient. Unfortunately, it is an irregular pattern in APX system. Next, it reads the descriptor of its own processor segment using the processor ID as index, and again sets the altered accessed flux. Now GDP can read the pointer to the object table directory, which can be specific to a particular processor. It can differ from the initial object directory, but in my system they are the same for simplicity. As I described, access segments are used to store pointers, or access descriptors in APX terminology. It's time to study them a bit. As I already mentioned, they implement a two-level access. A directory index is the index of the object table within the object directory, and a segment index which selects the entry inside that referenced object table. But besides addressing pointers encode capabilities, a set of writes, meaning the operations that code can perform using that pointer. Read and write permissions are obvious. The delete write relates to the pointer itself, not to the underlying object, if the code can delete pointer. Heap writes are used for local memory management, and that's another topic that I will skip, because I have not done any memory allocations from APX code. Last important field is system writes, which describes object-specific permissions. It is interpreted differently for different system types. For instance, here is the system writes encoding for the processor access segment. It declares whether an IPC message can be sent using that pointer to a processor object. Hopefully that makes sense and additionally reveals the complexity of the GDP. So after getting the object directory pointer, GDP reads the storage descriptor for the directory's own self-reference. I have no idea why, probably some internal validation. At this point the GDP can resolve physical addresses of different system objects. And it starts with reading the pointer to the processor data segment. It's different from the processor access segment that only holds pointers. Yeah, it sounds strange, but that's how the APX works. I used a single shared object table for all of my objects. I called it object table main. And again we see 5 bus operations for the table plus 3 more for the data segment address. The chip does have some caching, but it still feels wasteful. When processor data allocation obtained, GDP first logs that segment via hardware log, another quite high-level concept embedded directly in silicon. Then it again reads the processor data descriptor and sets the processor state to process selection, and the dispatching mode to normal mode. The mode determines which port and carrier will be used to dispatch the processor. I will describe that a bit later. By the way, here you can notice the descriptor cache at work. Even though the GDP already reads the pointer to the processor data segment, it does not re-evaluate it through the object tables, but works directly with the data segment. The local IPC message is kept inside the processor's local communication segment. So the GDP first resolves the address of that segment, then logs it, reads the IPC message. In my case it is a start processor message, marks the message as responded, and finally unlocks the local communication segment. Now the processor knows which IPC message it needs to process. It seems that the GDP has a very limited number of caches and internal registers, so a lot of state is kept in memory. In this case, it rereads the current processor status and sets it to the same value, process selection in normal mode, for whatever reason. Before we continue, let's quickly explain ports. The APX 432 systems uses asynchronous message-based communication for everything, not just between processes but also for scheduling. A port is basically a smart message queue. Sending operation is simple and straightforward. You just push a message. Receiving is more interesting. If the queue has a message, you get it immediately. If not, the consumer is suspended until one arrives. Internally, the port holds either waiting messages or waiting consumers. For dispatching ports, messages are enable processes and consumers are idle processors. JDP automatically tries to match them. If no work is available, processors wait in the queue. If all processors are busy, in that case, processes wait. It is very simplified because there is a lot more to consider. Priorities, conditional sense, surrogate messages, non-FIFO queues, etc. But even with that basic description, you can see that Intel literally built a whole operating system inside hardware. Fascinating. For regular inter-process communication, simple messages can be used. But for dispatching ports, it's a different story. We need to wrap process and processor objects into special wrappers called carriers. Again, it is a whole new topic because carriers are also used in a few other cases. But for our needs, we just have to fill some fields of the carrier object. With that background, the next log entries should make more sense. Before resuming the current process from the normal dispatching port, JDP first checks the delay port for any sleeping processes. APX supports a sleep instruction. When a process calls such instruction, JDP puts it into delay queue and periodically checks the timeout. Important detail about carriers. JDP doesn't create carriers on the fly. They must already exist in memory. And you can see it there. JDP grabs pointers to the delay carrier and the delay port. Note the 8-byte read instead of just 4-byte. Reclaims the delay port and sets the current port to the delay port. Then there is a sequence of operations to check if the delay queue is not empty. Read the pointer to the delay data segment from the axis segment, log the port, check various fields of the port related to the message queue, and finally unlock the port. The delay queue is empty, so processor can return to currently scheduled task. There is a field in the processor object that points to the current processor carrier. It's just a copy of the carrier pointer for the current dispatching mode. In my case, I pointed it at the normal mode carrier. For fault handling, the same field is also copied to current carrier. A carrier is basically an envelope, so it has to be unpacked. Because first revision has two distinct segment types, segments with pointers and scalar data segments. This takes several extra steps to read flags, offsets, statuses, etc. JDP clears the message present flag in the data segment and reads the pointer to the incoming message from the axis segment. So, what is this message? Surprise, surprise, it's another carrier. But in that case, it doesn't carry a message, it carries a process object. Carriers serve two roles, as message carriers and as object carriers. JDP stores the process carrier inside the processor object with proper reclamation, of course, and moves the processor state to the next stage, process binding. Information about current carrier is updated in the processor state. Previously it held a link to the processor carrier. Now it points to the process carrier. This field is intended for fault handling. It would be the fault handler's job to determine what is going on with the various structures in the processor state. By the way, we reclaim the process carrier again here, even though the reclamation flag is boolean and can only be set once. Wasted operations? No way. For that type of carrier, the JDP checks the maintenance request flag. And don't ask me what that flag is for. Then it logs the carrier and starts examining the process object to resume it. Just locking operation take 10 memory transactions. After locking, JDP checks information about scheduling periods and process status, and that's enough to decide if a process can be resumed or not. There is some synchronization between the process carrier and the dispatching port, but that's not relevant for the purpose of resuming the process. Finally, we are close to running real user code. Now I need to explain the hierarchy of user code and user data. Largest block of process is the context. It is a combination of code and data that can be efficiently addressed by that code. Closest analog would be a module or package. Context contains entry access segments, 4 lists of objects pointers that represent different lexical variable scopes. Also, it has a domain of definition that holds the actual instruction segments. Processes can have multiple contexts that call each other via inter-context calls. But I kept it simple. One context, one domain, one instruction segment, and a few data segments. Knowing that, we can decode the next actions of the GDP. It reads the current context that is executing within the process right now. When I mentioned scopes, I forgot to say that these scopes can be inherited from a higher context. For example, if one context calls another, the second context can inherit variables from the caller. And there are a bunch of mechanics to protect those scopes. For instance, we can deny modification of a segment representing a scope if the context nesting level is too high. And next few lines in the access log show these protection fields being filled in. But here is another funny detail. GDP first reads the pointer to the scope segment, and if it is a 0, the level is set to FFFF. But then it sets it to 0 anyway, even though it already knew that this value is 0 few cycles earlier. Another stuff that GDP wants to validate is the stack. There is a specific data segment reserved for this, and the information about the stack pointer and instruction pointer is kept inside the context data segment. Interesting detail is that the instruction pointer is a bit granular, because instructions can have variable bit lengths without alignment requirements. I guess it has been done that way to increase code density, but with trade-off of having much more complex decoding hardware. Finally, we're almost there. GDP reads the domain object, which contains an array of pointers to instruction segments, and reads the instruction segment itself. At that moment, the process is officially resumed and the processor state changes to process execution. GDP now starts executing instructions one by one, and the simplest instruction in my setup is return from context. Since I did not prepare any parent context, it immediately faults. So after all of that, dozens of memory accesses, multiple object tables, capability checks, hardware logs, carriers, ports, context, domains, and even a quick visit to the delay queue, iAPX 432 finally reached the very first user instruction. What we just saw is the real character of that processor. Incredibly ambitious object-oriented machine that literally implements large parts of the operating system in silicon. Every pointer is a protected capability. Every object lives inside a carefully guarded segment, and the CPU itself handles scheduling, message delivery, garbage collection, and permissions checking before it ever executes a single line of your code. It took a huge amount of prepared structures in memory and hundreds of bus transactions just to get from cold start to process execution step. And yet, it works. We successfully booted the GDP, fed it a proper IPC message, and made it run over our tiny test instruction. It is over-engineered, it's fascinating, and it's pure Intel ambition in hardware form from 80s. It was quite a journey just to run a single instruction, but I succeeded. Thank you for watching, and I hope it was not too boring. In the next video I will show how to actually write a real program for the iAPX 432. So stay tuned. See you soon. Bye.